Hello, my name is Jacob Varley, and this is Lab 3 Circuits. The purpose of this lab was to predict the behavior of circuits in parallel and in series, examine behaviors of resistors and capacitors, and to measure conventional currents and differences in potential energy. The current was the same before and after resistors, 0.02 amps. The voltage of the batteries was 3 volts in total. The resistors were measured to be 47 and 101 ohms, and then the charging and discharging time varied on the resistance of the bulbs. The fundamental principles used were the loop rule, the node rule, and the resistors, in addition to Ohm's law. So in the first part of the experiment, it was set up in the way that the picture in the top right details. The initial conditions were two 1.5 volt batteries, two resistors, 47 and 100 ohms, two ammeters, where the system is the circuit and the surroundings are, well, the surroundings. The predicted current can be found using Ohm's law, where we find the total resistance to be 147 ohms, and then we solve for I after measuring that the batteries are 3 volts, and we get a predicted current of 0.02 amps or 20 milliamps. Charge and energy conservation in series. So we converted an ammeter to a voltmeter. The ammeter reads 0 because the voltmeter has high resistance, and the voltmeter reads 3 volts because there's no other voltage drop or resistance. Where the results was that the current was 0.02 amps. The electric potential from A to B was positive 3 volts, no difference from B to C, negative 0.96 volts from C to D, 0 volts from D to E, negative 2.04 volts from E to F, and then 0 everywhere else. Using that, we calculated that the 47 ohm resistor had a resistance of 47 ohms, and that the 100 ohm resistor had a resistance of 101 ohms. We then found that the resistance of the wire and the ammeters were approximately 0 ohms. This is a graph of the potential energy versus the position and the circuit using the numbers that I just detailed. So what happens when you replace the voltmeter with an ammeter in parallel with the 100 ohm resistor? What happens to the current through the other ammeter and why? The ammeter has low resistance, so the electrons will flow through the ammeter instead, which will lower the overall resistance of the circuit. The total resistance of the circuit is now 47 ohms instead of 147 ohms, where the loop rule says that current is equal to 3 volts minus I times resistance, where we calculate I to be 0.06 amps instead of 0.02. In the second part of the experiment, we made an RC circuit where the surroundings were everything else. We used the same batteries. We used a capacitor and two light bulbs, one of 10 ohms and the other of 20. We connected each bulb to the battery circuit and measured the charging and discharging periods for each. After connecting the batteries to one of the bulbs, it dims with time. When you connect the capacitor to the bulb directly, the bulb gets brighter and then dimmer. The 10 ohm bulb charged in 20 seconds and discharged in 15. The 20 ohm bulb charged in 25 and discharged in 31. Possible sources of error include human error with the stopwatch and imprecisions of the ammeter and calculation roundings. What if you charged a capacitor without a resistor in the circuit? How quickly does the model predict it to charge? Would this prediction happen in real life? With no resistor, the ideal model predicts the instantaneous charge. Wouldn't happen in real life because batteries have internal resistances and wires have resistances as well, even if they're very small. Use an ammeter to measure how long it would take the capacitor to charge when connected directly to the battery. Why is the measured time different from predicted? When connected with an ammeter, the capacitor charges more slowly than predicted due to internal resistances in the circuit and non-ideal components. Thank you.